This system will notify you once you begin your broadcast. The broadcast is now starting. All attendees are in listen-only mode.
Hello everyone, welcome to the broadcast. Just going to wait for 30 more seconds to let a few more people join in. In the meantime, whoever is attending the webinar, could they just send me a quick hey or nay saying, just pointing out if you can see my screen and hear me properly? You can just type in the questions tab. I can see them here. Okay, good to know. All right, perfect. So a few more seconds and we get going. All right, perfect. Let's get started. Hello, everyone. Welcome to the broadcast. This is Devendra. I work with DataTorrent. I've been a data architect for quite some time, and I've been working with Apache Apex for a long amount of time. So let's take a look at what exactly is Apache Apex. It's a platform and a runtime that enables development of scalable and fault-tolerant distributed applications. What does that really mean? Is it a jargon, or is it really a engine that works very well? Yes, it is an engine that works really well in a distributed, scale-out, fault-tolerant fashion with the platform guarantees that are native to it. We just come to all the features in a little bit. It's Hadoop native. That means Apex leverages Yarn, which is a resource negotiator available with Hadoop, to its fullest. It's Yarn native and Hadoop native. It leverages Yarn for allocating containers and also for monitoring the running containers. It's a unified engine for both processing batch and streaming data. The philosophy that Apache Apex works on is that batch is just a unique subset of streaming, much unlike some of the other engines, which are sort of leaning on. I'm getting a few questions, but I'm going to take them in a little bit. Some of the other engines hinge on the thought process that batch can be addressed, streams can be addressed as unbounded batches. That's the philosophy that Spark Streaming 2.0 is leaning towards, where they're treating a stream as just infinite batch. Apache Apex and Flink and a few other systems basically treat batch as a subset of streaming. It's a high throughput and a low latency engine relying on in-memory computations. Along with the core engine, Apache Apex also open sources or provides a bunch of operators which are commonly used based on the access patterns or the designs that we see with high throughput distributed systems. There are a bunch of operators that have been open sourced along with, and the expectation coming out of an Apache Apex developer is just really to know Java and write your own application code. That being said, it's compatible with a few other languages also. I'm just going to pause and see if I have any questions. None at the moment. I'm going to go ahead. Coming to some of the features of Apache Apex. Apache Apex gives you ability for distributed processing. What this really means is that you can break down your application logic into these finite components called operators. Each operator is supposed to run a logical piece of code in a distributed fashion across your cluster. So the user writes an operator code, which is his or her implementation of the business logic, and Apache Apex takes care of running it in a distributed fault-tolerant way on your cluster. All the operators can be scaled up and down at runtime based on a user SLA. What this means is that at the start, when you're launching an application, you can say that an operator X would be spawned with 4 partitions or 4 unique instances of that operator. And then based on some user-defined SLAs, you can scale up and down during the course of the application run. Apache Apex takes care of negotiating the additional resources or scaling down the instances of the operator at runtime for you. Fault tolerance. This is the ability to recover from node outages. without having to reprocess from the start. Most of the other engines don't give this. So Apache Apex actually takes care of preserving the state out of the box, and this is really helpful for longer running applications. All the state of an operator all the state of all the operators across the DAG is checkpointed at runtime. Coming to the operator library, which we call Malhar, or the Apex operator library, most of the operators that are used commonly with respect to, let's say, JMS reads or JDBC reads or Kafka, Kinesis on the read side and the write side, and Hive, HBase, etc., are given out of the box. The expectation is that you can use Java to, just write your business logic, or there are a few scripting operators that work with Python. There's also a Scala API along with the Java API that we have. In addition to all of these open source things, DataTorrent as a company gives some enterprise offerings around operational insights, around monitoring, and ease of assembling an application. So that's available with the enterprise offering. I'm going to pause and take a few questions if there are any. Okay, I see. Does this work with Python and Scala too? Yes. There's a scripting operator in which you can write any Python code, and there's a Scala API that's exposed along with the compositional Java API that we have. Is this similar to Apache Storm? Well, in principle, yes, but there are a lot of architectural differences, especially around checkpointing and recovery. I will come to that in a little bit in due course of the webinar, Siva. Is Java only for a developer or other languages? There is a Scala API available, Sherful. When should we use Apache? When should you use Apex? So Apex core, and I'll just come to it, Pooja, and you'll see a few concrete use cases. So let's go through the other slides. All right. Here's an overview of the architecture and where Apex fits into the larger picture of the scheme of things, right? So Apex is capable of running in a physical or a virtual environment. So it can work with VMs or with physical servers. It can work on cloud and off cloud. So if a company has its own data center and physical servers, it can work there, or on cloud with Azure or AWS or Google Data Cloud. Any of these offerings, it can work. The only prerequisite that Apex has as a platform is having Hadoop 2.x, because it comes with Yarn, which is the resource negotiator. And Apex is Yarn native and Hadoop native, so it uses Yarn for negotiating resources to spawn the distributed containers for running the operators. We call them Yarn child in a distributed lingo, but that's the only prerequisite, Hadoop 2.x. And it's certified against all major Hadoop distros, which means that Cloudera offering any Hadoop version of 2.x or above, Apex can run on it very seamlessly. Hortonworks, Pivotal, MapR, etc. Like I said, only prerequisite 2.x. On top of Hadoop sits the streaming runtime, which is the Apex core engine. This is a high-performance, fault-tolerant engine that gives you that supports CEP and gives you in-memory processing for streaming data. On top of this engine, which gives you really good fault-tolerant guarantees, sits the open source operator library, or we call it Malhar. And your streaming application would be running on top of this streaming runtime or Apache core, while leveraging the offerings that come out of Malhar. On top of all these layers, DataTorrent as a company would give you, in the enterprise offering, would give you a graphical application design and launch tool, which is a drag and drop tool to assemble your applications really fast. And you get a visualization dashboard to see in-stream events. So your application would be a combination of operators or a directed acyclical graph of one operator to the other. You can see in-stream events using this visualization dashboard. In addition to this, making operability a bit easier, there would be a management console for making DevOps easier, just to see what throughput each and every operator is giving at an individual partition level as well as at a more logical operator level. This is to facilitate ease of operations and management. To interact with a running application, you have a REST API that comes with Apex to talk to the different components of a running application. So you can communicate with the STRAM using this REST API that is provided as a part of Apex. And this comes in the open source offering. Quickly going to take a few questions. I don't see any video presentation. Well, this is a webinar, Chaitanya. I can, sorry, Santosh. I can upload, I will upload the video of this at a later point. All right. So let's see how the operator library looks like. So in Malhar, we have identified the common usage patterns. So what we typically see with users is there would be an input, which would either read data from file systems or RDBMS or some NoSQL store. The common file systems we see are HDFS or sometimes even a local file system, and NFS and a few others. On the RDBMS side, we've seen MySQL and Oracle used more prominently than some of the other offerings. NoSQL, we have HBase, Hive, etc. Messaging, again, ActiveMQ, ZMQ, SQS from Amazon. So we've given out-of-the-box operators in Malhar to read from these sources, per se. Then we see a typical pattern of read from a source, parse, enhance, or enrich, and then do some computations, and then write to a destination. For all of these use cases, the more prominent technologies have been supported out of the box from Malhar with strong delivery guarantees. There are really robust operators for file system reads, for RDBMS reads, NoSQL reads, and JMS-based reads. And then we provide compute operators around pattern matching, stat and math, dimensions compute, as well as some in-memory store operators. On the right side, you have good operators for writing to Kafka, for writing to HDFS, and a bunch of other NoSQL stores like HBase, Hive, etc. Kafka read operators and Kinesis read operators give strong durability guarantees. They honor exactly one semantics and support idempotency as well as partitioning. All of these are available out of the box. A few of our customers are already using them with no custom code to read from Kafka, Kinesis, and file systems, and also to write to those sources. Let's take a look at how when we say native Hadoop integration, what does it really look like? I'll take questions after I complete this slide. So here's how your typical cluster would look like at a logical level. So here I have 4 data nodes. In Hadoop 2.x, you have a notion of a resource manager, which is Yarn, and a per node manager, which takes care of what's going on inside the node. So here you see the containers running off on Apex marked as green. So all the green boxes are Apex containers. So every application has a STRAM, which is a streaming application master, which takes care of governing or monitoring what's going on inside of the application. If a container goes down, then it's the responsibility of STRAM to negotiate for the resources for it from the resource manager. The STRAM continues to list every individual container, sends a heartbeat notification to the STRAM, and then based on that notification, STRAM basically will negotiate further resources from the resource manager if the container goes down. The boxes in pink are actually map tasks or reduced tasks running. This is basically done to showcase that an Apex application can run on your existing Hadoop cluster in a multi-tenant way with other MapReduce jobs or any other Hadoop processes that are running on your clusters. Here, one of the other things that is being showcased is the ability of Apex containers or Yarn childs to run natively in a distributed fashion. So, for example, here operator 1 and operator 2 are running on different nodes. The STRAM and operator 2 are running on the same node, so it's like node local in terms of affinity. Operator 3 and 5 are again running on the same node, and operator 4 and 6 are actually running as a part of the same JVM container. This kind of a locality is called container local. the flow of the application goes something like this. Operator 1 is reading data from an external source. So is operator 2. And operator 1 is then sending data to 3. 2 is also sending data to 3. Then 3 is giving a feedback to 5 and sending another stream to 4. And then operator 6 is writing something outside. There's a way to submit jobs to the resource manager using the Apex CLI. That's how your application would be launched. Stram is the entry point into the application, and the Stram would basically convert a logical plan into a physical plan and then negotiate the appropriate resources from the resource manager and continue monitoring a running application as it runs in a distributed environment. In addition to that, you get a DD gateway, which basically gives you an ability for to interact with the resource manager through a UI, and there's a DT console, which is the actual UI that sits on it. DT gateway is a RESTful service which enables you to interact with the resource manager and the application master through a RESTful API. Quickly going to take questions. I see it now. Thanks. All right. Is there any demo you can give? Yes, in some time. Whether it supports Kafka? Yes, very strong guarantees for Kafka. Support Cassandra? Yes, it does that too. There are Cassandra read and write operators, so you can read in a fault-tolerant way from Cassandra as well as write to it. Machine learning and algorithm, what algos are currently supported? There are a few algos around regression and variance that are supported. And you have integration with Samoa, which is a machine learning library. So good amount of support in that space, I would say. Available as computer. Is it capable to run it in parallel mode? Yes. Samoa integration gives you an ability to do that. Also, Apex gives you iteration support for iterative processing. So there's operator 1 and operator 2, and operator 2 can actually give a feedback to operator 1, even though it's a DAG-based model. So iteration support is very critical to machine learning libraries, and that's provided natively through the iteration support operators in Malhar. Let's move on to the next set of... So Apex follows this directed acyclic graph model. Think of it as a graph of vertices and edges connecting them. So your vertices would be operator or the business logic that you write, which will run in a distributed fashion on your cluster, and edges would be the streams that connect two different operators. So we call the edges a stream, which is essentially a sequence of data tuples that flow between different operators or logical blocks of processing. And an operator can take in one or more input streams, perform computations or the user's business logic, and then emit one or more output streams. Each operator would be your custom business logic written in Java, or Scala API is exposed, like I said earlier, or it could have a Python-based script that can be triggered as well. And you can have one or more operator instances, which is showcased here with the ellipsis format. This is how your typical DAG-based model would look like. So operator up. So just for nomenclature, I'm going to call the operator here that I'm pointing to as upstream, and the subsequent operator as downstream. So this is the most upstream operator in the DAG, and this is the most downstream operator in the DAG. I'll use this nomenclature in a few of the later slides where I explain partitioning and unification. Quickly going to take questions again. Apex would be a good replacement to Hortonworks Sandbox. I would say that depends on the use case. You can take the Apex Sandbox, it comes packaged with Hadoop, and you can start writing and running your distributed application on top of Apache Apex. So I would strongly recommend using the Apex Sandbox for writing your next distributed application. Any support for Kerberos? Yes, it's supported as a part of the enterprise offering with the security plugins we have. Let's take a look at the windowing support with Apex. So Apex natively supports sliding windows and tumbling windows. Here's an example of how data would be flowing through your application. The white circles represent tuples that are actually coming in, and all the tuples in green are what we call control tuples, which Apex uses for checkpointing what goes on in your application. These are just metadata or control tuples. They have no significant or any overhead on what's going on in your application, and they have no data inside them. So don't worry about increasing latencies or anything of that sort. Here's an example. So we're saying that the application window, which is the difference between a begin window and an end window, is 0.5 seconds or 500 milliseconds. And what we're doing here is that we're marking a begin window and an end window, and we are processing something between the two. At between n begin windows and end windows, we trigger what we call a checkpoint tuple. Once this checkpoint tuple flows through different operators in your DAG, each operator snapshots its state. So all the non-transient variables in your operator will be checkpointed initially to the local disk, and from that point on, there's an asynchronous daemon that copies them over to HDFS. So your local operator is not burdened with the additional responsibility of making a HDFS call. This checkpoint tuple will basically trigger that function to checkpoint the state locally and then copy it asynchronously to HDFS. This works very well in a scale-out architecture wherein you're running thousands of containers and each of them is carrying a significant amount of state that needs to be checkpointed, because then you're doing asynchronous writes and you can still leverage the efficiency of having a distributed checkpoint. This is very unlike some of the other systems which either rely on an ACK-based system or rely on the fact that you have to checkpoint the entire state of a RDD at every single hop. Apex works on the notion of incremental checkpoints. So after a particular window has been committed across the DAG, you can actually purge the data that was before. So you are only dealing with the last incremental checkpoint and not going all the way back to the input source and rewinding all the tuples that you have processed. Quickly going to take a few questions again. Are there any good open source projects using Apex? Apex integrates with a bunch of open source projects, if I understand the question correctly, Chaitanya. If the question is, does any other open source project import Apex natively? I am not sure if that is correct, but yeah, Apex integrates with a bunch of projects. I can share a link at the end of the presentation. Does this sort of on Lambda architecture? Does this work on Lambda architecture? Well, yes, you can. You can do. So let's go back to the DAG model, Siva. So one of the forks of your operator, one of the forks that you read from could be a streaming source like Kafka, and the other source could be a file-based source, right? So file-based sources are typically files are written in batches, and you can still read that from one fork of your DAG, and you could read in a streaming way from the other fork. So you're doing sort of a Lambda architecture within a single app. You don't have to worry about specifying a different streaming pipeline and a different batch pipeline. That would be taken care of natively by Apex. So yes, I would say, yeah, you can create a Lambda fork through this. Yeah. Okay, going to move on to the next set of things. Here's an application in Java, a typical application that you most commonly see. You're reading from some input source, parsing the records, emitting some words out of it, counting them, and writing to a console. So this is your hello world of the big data space, also called as word count, right? We all, irrespective of the technology in big data we are working on, this is your gateway to that technology, right? So in Apex world, what you have to do to write such an application is you have to implement the streaming application interface, which gives you a populate DAG method. So essentially, you're going on and adding operators to the DAG. Yeah. Oh, sorry. People are not able to hear my voice. Are you able to hear my voice now, or has something gone wrong? Can someone else ping me? Okay, I'm gonna continue. Yeah, I will share the slides after. All right. Okay, let's get back to this. So populate DAG method gives you an ability to add different operators, which are the vertices in your directed acyclic graph or DAG, and the edges or the streams that connect them. So let's take a look at this particular example, right? So your operators or your edges of the graph would be an input operator, a parser, a counter, and a console operator, right? So here's what I'm doing in the first four lines of this function. I'm creating a line reader, which would be reading lines from HDFS or my local file system. A parser, which would parse those the incoming lines into individual words. A unique counter, which would count the number of unique words that I'm seeing, and a console output operator, which would essentially just display the counts and the words on the console. After doing this, what I'm doing is I'm just adding those four operators to a DAG, and the interface that you would see is that an upstream operator's output port connects to a downstream operator's input port. That's how you connect one vertex to the other, or one operator to the other. So the point of connect is what you call output port. So what I'm doing is I'm connecting the output port of the first operator or the upstream operator to the input port of the downstream operator. So in this case, I'm doing line reader.output connects to parser.input, and I'm calling it a stream. So I'm naming the stream as lines stream, and line reader's output port connects to parser's input port. Then the next stream is words, and the parser's output port connects to counter's data port. Essentially an input port. I can call the ports whatever I want to. It's a variable name. And then the counter's output port goes to the console operator's input port. This way you have connected an application, and then you can just use the Apex CLI or the gateway or the REST APIs to launch an application. Yeah. Let's take a look at how an operator actually looks like. It's very easy to extend operators and write your own business logic in them. Molar gives you a base operator implementation, and what you have to do is you have to add an input port to it and an output port to it if you need to. So basically here I'm adding a default input port that takes a string input, and I'm overriding the process tuple method that comes with the default input port. So for an incoming string, I'm splitting it into based on some punctuation marks or spaces, and then emitting individual words out of it. If you notice here, I'm saying output.emit, which is the default output port. So let's go back to this guy. So the parser, it's getting some data on the input port and emitting words, right? So the input port here is input, and the output port here is output. So I'm getting some tuples on the input port, parsing them and splitting them, and then emitting them out of the output port. I'll take questions after the next slide. Here's another implementation of a base operator. It's called like a unique counter. I'm maintaining a map of unique words that I'm seeing with a count associated with them. And at every end window, what I'm doing is I'm just creating a key value pair of the word with the number of counts that I'm seeing, and then flushing that map. So I'm actually not clearing the map at any point, so it's a cumulative count. This has been done to showcase that it's actually stateful, right? So till the end of Windows 5, if the count of key 1 was 20, and in the sixth window, if I get five more keys of type K1, then I'm keeping that count as 25 and emitting 25 instead. This is just another way to give arguments to the process tuple method using the latest Java APIs. Again, I have an output port which would be emitting the key value pairs that I'm generating. Quickly going to take questions. All right, I think I missed a few here before I said. Okay, I'm going to move on here. All right. We can hear you. Okay, I have a question. Is this similar architecture of spouts and bolts? Yes, in a sense, it's pretty similar, except spout is just an input operator. So there are there are different kinds of operators in Apex. One of the types is an intermediate operator, and there is input adapter and output adapter. So an input adapter would not have any input port, which is similar to a spout. And an intermediate operator is something like a bolt in Storm, and an output adapter would not have any output port because it's going to write to the external system. Yeah, so in a sense, it's pretty similar. Yeah. Moving on to the next slide. Let's see how a distributed application would work really, right? So here is how a DAG would look like if it has three operators. So I have operator 0 here, operator 1 here, and operator 2 here. This is just a logical view of the DAG, but in reality, when I'm running a distributed application, I would want to have multiple instances of one operator to scale out and parallelize my operations, right? So when I translate that logical operator to a physical one, and I say that, okay, operator 1, I want 3 partitions for it to run on my actual cluster, then the diagram would look something like this. Operator 0 is talking to 3 partitions of operator 1. And then let's say I want only 1 partition of operator 2, then I need a mechanism to unify all the inputs that go to operator 2. There comes this concept of unifier. A unifier logically is going to be similar to a combiner with MapReduce, but physically could be located anywhere. So if you guys are aware of the MapReduce paradigm, a combiner is like your local reducer. So an output of a map task would go to a combiner. The combiner would run the reducer code locally and then just send all those reduced tuples across the wire. So the purpose of a unifier or a combiner is really to reduce the network shuffle. Similarly, in Apex terminology, you have the unifier, which is going to reduce your shuffle across the network as well as unify the tuples that go into a downstream operator. Partitioning can be of 2 types really, n cross m or parallel partitions. So in an n cross m partitions, you have n instances of the upstream operator and m instances of the downstream operator. For example, let's look at the example that we have here. You have 4 operators in this DAG 0, 2, 3. And what I'm saying here is that in the physical DAG, I have 3 instances of operator 1 or 3 partitions of operator 1, 1A, 1B, and 1C. And then I'm unifying them before sending it to 2 instances of operator 2, which is 2A and 2B. And then I'm unifying the output of operator 2 to make it talk to a single instance of operator 3. Now, Apex can actually reduce this bottleneck of a single unifier, taking in all the writes from the upstream operators by introducing multiple unifiers. There's a concept of a stream codec and a hash function that goes along with it, along with a mask, to make sure that the unifiers read unique data coming out of operators 1A, 1B, and 1C. So in the bottom figure that you see here, a third of the data from all of these operators would be going to unifier blue and unifier green here, and then 2A and 2B are essentially reading in a parallel way from the blue unifier and the green unifier respectively before sending them to a single unifier before operator 3. This way you're reducing the load coming on this unifier, which was becoming the bottleneck. Quickly going to take questions before I move on. IOX. I'm not following this nomenclature, Lucia. Could you just elaborate? I'll take your question after the next one. I don't follow the nomenclature IOX. If any of the other participants do, please feel free to drop in and I'm happy to answer. All right, moving on to the next slide. Let's take a look at the partitioning support that's available with Apex. Like I said earlier, n cross m is supported, so n instances of the upstream operator and m of the downstream one. Let's just take a look here. Let's say I have 2 instances of, or 2 partitions of operator 1 and 1 instance or partition of operator 0. And then I'm unifying the output of operator 1 to go into operators 2, 3, and 4. Here we are showcasing that unifier after operator 1 is becoming a bottleneck. So Apex as a platform can give you this notion of parallel partitions. So what we're doing is we are saying that operator 1 and 2 are in parallel partition, and then everything downstream is in parallel partition. This way we are essentially creating multiple partitions of 2, 3, and 4 to ensure that your unification bottleneck goes away, and all the tuples from 1A just go in a sticky way to 2A, and all the tuples from 1B go in a sticky way to 2B. That way, parallelizing what's going on in your distributed application and giving you a very high throughput without any trade-off on latencies. After 3A, we are putting in another unifier because let's say you have given operator 3 and 4 to be in N cross M partition. So that way you have the ability to give different partitioning schemes within the same DAG. For example, in this case, operators 0 and 1 are in N cross M partitioning scheme. Operators 1 and 2 are in parallel partitioning scheme. Operators 2 and 3 again are in parallel partitioning scheme. And then 3 and 4 are in N cross M partitioning scheme. These are literally just a few configuration settings that you have to do. No user code is absolutely is required for doing any of these partitioning schemes. So if you can appreciate, scale out becomes really easy, leveraging the options that Apex gives you natively. Let's take a look at how a unifier would look like. So here's the logical plan of two operators. I have an upstream operator and a downstream operator. And I'm saying that I want 4 partitions of the upstream operator pumping data into one partition of the downstream operator. Now, in this case, it's likely that the unifier that's inserted by the platform could become a bottleneck. So since you have 4 instances running possibly on different machines of the cluster, talking to a single unifier, your network interface card would become a bottleneck. This is a lot of shuffle that goes between an upstream operator to a downstream operator. So your NIC could end up becoming a bottleneck. In this case, Apex as a platform can insert what you call cascading unifiers, or a hierarchy of unifiers, to make sure that upstream operators partition 1 and 2 go over one NIC to a unifier, and then that unifier's output goes over another NIC, so that a single NIC doesn't become a bottleneck, or a single unifier doesn't become a bottleneck. A cascading unifier is inserted by the platform natively, so you don't have to worry about scale out even at a unification level. This is very unlike how a combiner works. A combiner is just local to the node where your map task is, and there is no notion of cascading combiners. So for large shuffle use cases, cascading unifiers work really well. Quickly going to take questions. How are node failures handled in Apex? Yes, Apex maintains the notion of a state, which basically means that in the checkpoints, Apex is snapshotting the state of an operator. And if a node goes down, then application master would know that a node has gone down and all the operators on it have gone down with it. So there is a replay mechanism that happens once an operator comes up from the last checkpointed state, and then all the tuples after the checkpointed state would be replayed. Do we have control over how a partition should happen? Yes, you do have control. So there are 2 ways to partition operators in Apex. One is called the static partitioning, and the other one is dynamic partitioning. Static partitioning essentially means that you know how many partitions of an operator you would need based on some throughput benchmarks that you have done. Let's say I want 4 partitions of operator 1, and I say the partitioning scheme is static. Then your runtime application would only have 4 partitions forever. The other way is to have dynamic partitioning, which means that based on the input throughput or some SLA based criteria, you want to scale the number of partitions of operator 1 up and down. So that can also be achieved. There are APIs to do that with Apex. Very minimal code to write. And dynamic partitioning is supported with some of the more popular operators out of the box. For example, the Kafka operators or Kinesis operators give you dynamic partitioning from Malhar itself. Is there a concept of secondary name node in Apex? Well, I would say Well, Apex is something that runs on top of your Hadoop cluster, right? But I'm going to interpret this question as being: is there a concept of HA in Apex, right? Or what happens if the streaming application master goes down? So if the state of the streaming application master is also checkpointed, and if it goes down, you recover it from the checkpointed state. Yarn by itself can give you ability to do a restart on an application master. The default is 2. So if an application master is killed and goes down, then Apex recovers it once. If it goes down again, then it does not. But that's a setting on the yarn side. If you increase that from number 2 to number 10, then this process would happen 10 times. So yarn by itself gives you that ability, and Apex honors that while giving you the extra benefit of a checkpointed application master state to recover from such failures. Yeah. Does this snapshot happen for data name nodes? Santosh, the snapshots happen for an application, for an operator state, right? So you don't snapshot a data node or a name node. Your application is running as individual operators or individual yarn containers in a distributed way. Their state is snapshotted onto Hadoop eventually. So yeah, your state would be on Hadoop, but yeah, you wouldn't snapshot a data node as such. All right, I'm going to move on to the next slides. Just going to take a quick break for some little water. I'm sorry. Yeah. So let's take a look at dynamic partitioning. So like I said earlier, dynamic partitioning is the ability to scale up the number of partitions of an operator on the fly based on some SLA. For example, if you're reading from Kafka and you only have 2 partitions reading from 128 partitions of your topic, and you want to make sure that your latency does not increase beyond, let's say, 20 seconds, and the data pumping in your Kafka clusters is increasing by the second, then you can actually have a latency-based criteria here saying, if my latencies go above 20 seconds, then I want 4 or 8 instances of this operator. Apex can do that at runtime. There's a simple API for a custom scaler or partitioner that Apex gives you. In this figure, I'm not showing any unifiers because they just clutter the figure. So at stage 1, let's say I have 2 instances of operator 1A and 2 of 1, and 2 instances of operator 2 and 1 instance of 3. Let's say I want to scale up operator 2 at runtime, then I can do that. And Apex takes care of snapshotting the state and relaying the state when a new instance of operator 2 is created. So in this figure, operator 2C and 2D are the actual physical instances of operator 2 that are created afresh or by Stram after negotiating new resources for them from Yarn. And then Apex as a platform would initiate those operators at an appropriate state to make sure that they are not duplicating any data or they're not reading any data that you don't need them to read. Simple and elegant interfaces are given for this to make sure that their state is initiated from a particular point of snapshot. And then again, after a while, you may want to scale up instances of operator 3A and 3B also. No new questions, I suppose. So I'm going to move on. I can give you a dynamic partitioning example at the end of the slide. Now, let's take a look at how partitioning actually works, right? So I have an upstream operator and I have one or more downstream operators. The upstream operator is relaying data to the downstream operators. Now, let's say I have one upstream operator and 4 downstream. I want each of the downstream operators to read only a subset of a distinct subset or a disjoint subset of the upstream operator's data. How can I achieve this? So every tuple that goes out has a notion of a hash code. This is a Java hash code supported by Java natively. So you don't have to do any extra work for this. And then on the downstream side, there's a notion of a hash map. So let's say you have a tuple that's flowing from an upstream operator to one or more downstream operators that looks something like this, has a name and some address and some pin code. Then then you apply a hash code, which is your Java hash code on it. It generates a sequence of bytes, and then each of the downstream operators will apply a mask on it. So this is just a AND mask. So each of the upstream operators would apply a 2-bit mask to it. And if the resultant bit computation is 0, 1, then I know that my partition 2 of the downstream operator has to consume this. Every upstream operator has a buffer server sitting on its output port, which would keep these tuples, and then downstream operator subscribes to that, applies its mask, and then it knows which tuples to consume out of all the outgoing tuples that are broadcasted from the upstream operator. So you have exactly disjoint subset of tuples flowing into each of the downstream operators. This is what we saw in the earlier dynamic partitioning example as well. So if you notice here, 2A output from 1A is going to different instances of 2, right? So all 4 instances of 2 are consuming only a distinct subset of tuples coming on from operator 1A. All right, I'm going to move on. No new questions. So you have the ability of specifying custom partitioning as well. So here I'm just showcasing how you can do a broadcast, right? So the default that Apex gives you as a platform is a hash-based partitioning scheme. So the incoming tuple would be subjected to a hash function, and the downstream operators would apply a mask depending on the number of bits that goes up in powers of 2 to ensure that a downstream operator reads only a unique tuple coming from the upstream one. In this particular case, we are changing that default behavior to showcase that you're reading a broadcast message. So every downstream operator would be consuming exactly the same message. So it's a bitwise with 2 zeros here to make sure that there is no mask, and each downstream operator's partition would receive exactly the same tuple coming out of the upstream operator. I'm going to take a few questions before I move on. No new questions. All right. Let's take a look at the fault tolerance semantics. So like I mentioned earlier, Apex checkpoints the state of an operator. So there's a control tuple called checkpoint that flows from an operator, flows through all the operators in a DAG. So the default checkpoint interval is 30 seconds, but it's configurable. So if you need less frequent checkpoints, you can do that with configuration settings that can be changed at runtime as well. So checkpoint is performed automatically by the engine, and the user really doesn't need to write any code for this. After an operator receives the checkpoint tuple, it will checkpoint all its non-transient variables into the local file system at first, and from there there's an asynchronous daemon that basically will copy it to HDFS. If an operator fails, then Apex initiates a recovery from the checkpointed state. I'm going to take a question because I'm seeing quite a few buzzing now. What is the real need for Apex when there are Spark, Flink on top of Hadoop? No, I'll come to that. Don't worry about it. This Santosh, good question. In case, the frequency of checkpoints is configurable, and the default store for it is HDFS. But if you need any other store, there are pluggable interfaces that you can extend and write to different stores. There is an implementation for Geode, which is an in-memory data grid available with Malhar already. There is a heartbeat detection and recovery mechanism that's followed by STRAM to detect if a node has gone down, if an operator has gone down or not, and then the STRAM will basically negotiate further resources for it from Yarn. There's also a buffering mechanism to ensure replay of data from a checkpoint. So there is absolutely no loss of data. This buffering mechanism is done using a buffer server, and the application master state is checkpointed. So we basically ensure that application master, which is really the governing daemon or the guy who's taking care of monitoring how your distributed application is running, is checkpointed, and it in itself is fault tolerant as well. So if the app master goes down, its state is checkpointed, it'll come back up from that checkpointed state. So the app master will have a context of where your yarn child or containers are running, and it'll take care of the heartbeat protocol and fault tolerance mechanism from that point on. Let's take a look at how Apex really handles checkpointing and back pressure. So checkpointing and back pressure handling is done using a component called buffer server. This comes with the Apex core engine. Think of a buffer server as an in-memory Kafka, which follows a publisher and a subscriber mechanism. So here, buffer server basically sits in the same JVM or the same container as the upstream operator's output port. So each output port for an upstream operator would have a buffer server associated with it. The upstream operator publishes to a queue in the buffer server, and the downstream operator consumes from that queue in the buffer server. How does a downstream operator know which queue to connect to? You have one downstream operator connecting to an upstream operator's output port, right? And then based on that, you basically know which buffer server you're talking to, and then different physical instances of the downstream operator know which tuples to consume based on the hash code and mask mechanism that we saw earlier. So there is no data duplication using buffer servers. Now, the buffer server handles back pressure in Apex. So let's say the downstream operator goes down and the upstream operator is still pumping data, which is going into the buffer server at first, and no one is consuming it, then the buffer server spills over to the local disk. The buffer server is really useful for maintaining ordering and idempotency as well, because it maintains the order of messages as it writes data to one of its queues. Quickly going to take questions because this is an important topic. A buffer server is like memory channel. Actually, no, I would say buffer server is closer to an in-memory Kafka in terms of its semantics. Flume memory channel is just a single queue in memory, whereas buffer server gives you the ability to have multiple queues in a memory context that spills onto disk. Yeah. Is there a transactional support and like ability to roll back, etc.? I would say, well, in a different way, really, because you can do a replay mechanism in Apex, which the platform does natively. So if an operator and I'll come to it actually in the next slide to put it into context in recovery sense. So let's say I have an end window tuple for window 2, and then I have two tuples with count 1 in it and count 3 in it, and then I have another begin window and then end windows following after it. Let's say at the end of the second window, my sum is 7. So I have a variable inside my operator, just a basic operator for counting a sum for something that keeps a value 7, and then my operator goes down. Now, what would happen is that you would recover the operator from the checkpointed state, and you would replay the incremental tuples that you wanted to read but could not from the buffer server, and you basically would start at sum 7 and then just apply 1 and 3, which is what you did not see, to the base number, which is 7. This way, you're not going back to the start where you arrived at the number 7, 4 to 1, you arrived at 7. You are essentially keeping the value 7 as is, and then you don't have to worry about replaying 4 to 1. Instead, you would just replay the tuple 3 from the buffer server, and you would arrive at a count 10. So you are being stateful as you go along. I'm going to take another question. Can you please be loud when repeating the question? At times it... All right, sir, I will do that. Can we configure the buffer server like number of queues, size, spill threshold, etc.? Yes, there is an ability to specify the memory and the size of queues with Apex servers. Yes, that would basically give you the ability to keep more stuff in memory in the in-memory queue of the buffer server than to spill over. Yeah, you can do that. Let's see the different processing guarantees that Apex gives you. So Apex gives you at least once, at most once, and end-to-end exactly once. So just a deeper look into at least once semantics that Apex gives you. So with at least once semantics, on recovery, your data will be replayed from the previous checkpoint state. Messages will not be lost because buffer server will replay them from the previous checkpointed state. Now the question is, when does a buffer server actually purge the messages? And the answer to that is that a buffer server would only purge messages after a window has been successfully processed by every operator in your application, and then a committed callback is initiated by the platform, and after that the data associated with a particular window is deleted. Till that time, all of the data would be in the context of a buffer server. This is the default, like at least one semantics is the default behavior or mechanism that we see with most applications, and it's usually suitable for a lot of applications. This can be used in conjunction with with idempotency to achieve exactly one semantics. Usually we see exactly one's behavior being required in transactions with which deal with meta information or rewinding outputs from an external store. At most once on this, the recovery will just be initiated from the last state of the operator. So there is no replay as such. You are going to recover. You're going to start the operator from the state that it is. It's useful in cases where some data loss is acceptable, but you don't really replay anything from checkpoint. You just start the operator from after resources from it are negotiated. Exactly once. Now let's take a look at what exactly once really means, right? You're reading from an external store, let's say a file system, and you are in the middle of reading a file and your operator goes down. You have read 1,000 lines of a file and you don't want to read those 1,000 again. You want to start from 1,001th line of the file. Now this is exactly once semantics. Apex gives you the ability to do that. So when you do at least once and you add a logic for a state recovery to your operator, then you can achieve end-to-end exactly once. Usually exactly once is dependent on the external systems. Some systems like Kafka or Kinesis have notion of offsets or sequence numbers to enable you to achieve exactly once semantics. Even with files, you can do that, wherein you can keep a track of how many offsets you have read from the files. The operators which are available out of the box with Malhar for Kafka reads and Kafka writes and Kinesis reads and file system reads and writes give you the ability to achieve exactly once out of the box. There's a JDBC one that's coming up, which will also achieve those semantics. That being said, exactly once behavior is usually governed by the interfaces exposed by external systems, both on the input and the output side. So Apex gives the operator user ability to keep state in order to achieve that. Let's take a look at stream locality. So stream locality is the ability of an operators to be co-located in a way. So the default locality that we saw earlier, there are 4 types of localities really. Your operators could be rack local, meaning data doesn't have to go across a network switch in that case. So 2 operators running on the same rack. For example, an operator consuming data from Kafka and sending it to another operator, which is decompressing and parsing those messages. It's better to have them on the same node at least, so there isn't a lot of outbound traffic passing a network switch. The other locality mechanism, this is node local network interface card. The other mechanism is a rack local interface, wherein you don't want 2 operators that are exchanging a lot of data to cross a network switch. For node local, it's a network interface card, which could be a bottleneck. The third mechanism could be a container local operator. Again, let's take an example of data coming in from a Kafka input operator and sending data to a decompress operator. Now, these 2 operators can be container local, as in Kafka input operators are usually IO intensive, and the decompressor would be a CPU intensive operator. So these 2 can coexist in the same JVM. This way you prevent serialization and deserialization of Java objects as they travel between 2 operators. The fourth mechanism could be a thread local, right? Which basically means that 2 operators are in the same JVM, yes, but they are also in the same function call stack. So essentially, one operator is going to be called after the other operator, just like 2 functions are being called. Again, no serialization, deserialization, and the same function call stack would be used for exchanging messages between the two operators. This is really fast and can be used for use cases which require very low latency operations between them. I'm going to take some questions before I move on to the next set of things. No questions right now. Going to move on. Quick checkpoint, guys. 15 more minutes, I would say. Let's just take a look at the more commonly used use cases that we see with some of our customers or in general in the big data world. So typically you ingest data from one or more popular sources like IoT logs from some WebSockets or from Kafka, or files, batch ingestion using files, or some social media logs. Apex treats streams as a superset of batches and not the other way around. This is a philosophy that we see coming up with some of the other streaming systems like Spark Streaming, where they're saying a batch is an unbounded stream. So they rely on the philosophy of cutting up a stream into an infinite number of batches, whereas Apex and Flink and Storm treat streams as a superset of batches. You will see this stream as a superset of batches being adopted more widely than the other philosophy of which Spark Streaming seems to be going towards. So Apex does in-memory processing based on windows that we saw earlier, and you can apply stateful operations around aggregation and CEP rules for analytics with Apex. So here's a simple architecture. You're reading some browser logs from Kafka. Then you're using the Kafka input operator to do that. You're decompressing and parsing those logs, probably filtering them, forking them into multiple pipelines, and then you're running your dimensions aggregate and talking to an external interface using, again, a Kafka-based pub/sub mechanism. So you're reading from one or more sources, enriching, aggregating, and writing to one or more sources. So to answer one of the other viewers' questions, these are the kind of typical use cases that you would see with streaming analytics. Let's take a look at batch versus streaming, really. So if you look at Spark versus Apex or Flink or Storm or Samza, Spark follows this notion of micro batches, which basically means that you have one large batch of, let's say, a million events in the MapReduce world. Spark Streaming takes the approach of chopping that batch into smaller batches, let's say of 1,000 events each, and then scheduling those as separate tasks using a DAG scheduler. Here's an example. Your receiver is receiving a bunch of records. Now, instead of creating batches of 10,000, you're going to create batches of 1,000. You will have 10 of those batches to schedule on different nodes and process them in a parallel way. So this is the architecture that Spark follows. A simple example with a real world use case would be, let's say you're running a factory and I have 4 workers doing 4 individual tasks. Let's say worker 1 is assembling part 1 into part 2, and then worker 2 is assembling part 3 into the output of the output that worker 1 is giving him. Now, Spark Streaming goes with the approach that worker 1 is not going to send any of the parts to worker 2 until he gets 100 parts assembled. Now, this is latent by itself because worker 2 is going to be idle until it gets those 100 parts from worker 1. Whereas this is not a prerequisite, right? Worker 2 can start working on the first part as soon as worker 1 finishes it. This is your typical assembly line approach that's followed by Apex. So input tuples coming in, no one has to wait for the 1,000 tuple to be processed by the source operator till any of the downstream operators can receive it. So the source operator will relay operator 1 as soon as it receives and processes it, and the downstream operator can work on it as soon as it receives it too. This is an assembly line example again, where worker 1 is assembling parts 1 into 2 and then moving it quickly to worker 2, where worker 2 can start assembling part 3 into it and then move it to the next worker in the chain. This way, no artificial latency is introduced. And to keep a track of all the checkpointing and metadata operations, the platform inserts these control tuples for maintaining state. So there is no artificial latency or overhead in terms of the operations that there are. Let's take a look at, I'm just going to see if there are any more questions. None at the moment. I'm going to move on. All right. So let's take a look at the architectural differences between Spark Streaming and Apex. Quickly going to pause for a water. All right. So in terms of the processing model, right? So Spark Streaming, while you could go theoretically to really, really small batches, it's still micro batch. You're not, if your micro batch duration is a second, or it's based on a size of 1,000 events, your next operator or the next executor is not going to receive anything till the upstream operator or an executor processes all those 1,000 events, or there will be a latency of a 1 second till the next operator can receive anything. Apex is native streaming, it's data in motion. So as soon as operator 1 flows through the first operator, it's going to go to the second operator, and metadata operations will happen in transit or by the platform natively. Let's take a look at the language support. So Spark Streaming supports a Java-based API, a Scala-based API, and there are a bunch of other client bindings for Python support and R support and a few other things. Apex has a very strong Java-based API, and it has a Scala-based API as well for Scala developers to assemble tags and write operator codes as well. So this is language support. In terms of the API support, Spark Streaming follows what you say a declarative API, which is a higher level API essentially. Declarative APIs typically follow the dub model, which is read from somewhere, dot parse this, dot aggregate, dot map, dot reduce, dot write. So this is like read from, dot write from API. It's essentially a higher level API which gives you ease of assembly in a way if your operators or the RDDs that you want to use are available out of the box, but is very restrictive for true production systems, wherein you would see more intricate business logic going into your individual building blocks, and writing those RDDs, writing a custom RDD becomes a bit more intricate and tedious, and then assembling it may not be the most intuitive. Typically, the production systems that you see will not run on something as simple or as naive as read dot map dot reduce dot write. It's more for POC or prototyping purposes, I would say. Apex has a compositional API, which is sort of a lower level API. An example of which we saw earlier, wherein you were pulling in operators and then assembling them, connecting them using streams, and then you could set locality and partitioning scheme on the streams. This is typically the way you would be assembling or writing a distributed application. Gives you more granular control towards pulling in your own custom operators from the business logic that you have written inside them. In addition to this, for ease of use and for enabling data scientists and rapid prototyping, Apex is now providing a declarative API, which is the first few drafts of it are available, and it's getting stronger by subsequent releases. So Apex will also have the ability to read from somewhere, dot parse, dot filter, dot map, and there is also windowed operators coming out for windowed operations to be provided natively using Apex. Quickly going to pause and see if there are any more questions. None at the moment. All right. Let's take a look at data locality, right? Like I mentioned earlier, data locality is critical to optimize the shuffle that goes on between different operators, or the shuffle that goes on while running a distributed application. So data locality can be node local, rack local, container local, and thread local. So Spark Streaming gives you the advantage of data locality because it's a batch scheduler, right? So the DAG scheduler in Apex in Spark Streaming can essentially keep on scheduling your executors where your data is located. This works out pretty well for Spark Streaming, and it's really a theoretical concept because data locality in the Spark Streaming context does not work very well when you are running thousands of executors. I'll give you an example of this. There are two concepts that go around this. There is taking data to compute, and there is taking compute to data. So Spark streaming works on the principle of taking compute to data. Now, consider this use case where all of your data is queued on a few data nodes. Spark streaming will keep on scheduling jobs on those data nodes to leverage data locality. While this may work very well for evenly distributed data, and it usually doesn't work very well in cases where you have thousands of executors running and your data is queued, because then your DAG scheduler is going to keep on scheduling data on that specific node. The result of it will be that your DAG scheduler queues will get tasks will get queued up in your DAG scheduler, and they'll never be scheduled, again increasing latency, right? While your throughput will be high once a task is scheduled there, your throughput is going to come at a cost of latency, because your tasks are just going to be queued up and they will not be scheduled to run as such. Apex works on the principle of taking data in motion, or taking data to compute. This works very well for scale out architectures. If you're running thousands of nodes crunching terabytes of data, then you will have these operators running in a distributed way on your cluster, and then you're just taking pieces of data and relaying them to those containers. So in a scale out architecture sense, taking data to compute works better than taking compute to data. Let's take a look at latency. Like I mentioned, Spark streaming is a micro batch model, so every hop introduces some latency. So latencies in Spark are very usually in the seconds time frame, 1 or 2 seconds, depending on the batch sizes that you give or the batch interval that you give. Latencies in Apex are typically in millisecond range. So the default window size is like 500 milliseconds. That can go down as well. And Apex really doesn't introduce any artificial latencies. So you could have, we have actually seen applications do 10 milliseconds and 15 milliseconds for end-to-end latency in a DAG, since there is no artificial latency introduced. Now, throughput and latency are sort of, go hand in hand. Spark streaming can do very high throughput, but the cost of it is with a latency trade-off. Now, if you keep on scheduling the same tasks on the same nodes where your data is residing, your throughput is going to be immense. So theoretically, Spark can achieve very, very high throughput, because the batch scheduler is going to keep on scheduling new tasks as you have more and more data. But the flip side of it is that the throughput versus latency graph is going to be exponential. So as your throughput is going up, your latency will end up going up, and that typically would not be very acceptable in a distributed application with very tight SLAs. Whereas in Apex, your throughput versus latency graph would look very, very horizontal. Linear is a good state to have, but Apex gets you one up and it takes you more horizontal. So your latencies are going to remain constant as your throughput increases. That's the advantage of taking data to compute and giving a truly distributed checkpointing mechanism for a scale out architecture. So scalability. So Spark, the DAG scheduler that basically schedules different tasks on Spark, becomes a bottleneck when you have hundreds of partitions and thousands of containers running inside your Spark cluster. The DAG scheduler has to negotiate every single micro batch. So if I have 1,000 executors, they're running my micro batches of 1 second. Every second, I have to make sure that I'm able to schedule 1,000 tasks with my scheduler on my cluster. This is a lot of chattiness and a lot of resource negotiation that goes on with either Yarn or Mesos or its native scheduler, its native negotiator that Spark gives. So scheduler usually would become a bottleneck when you're running several hundred containers with Spark. Partitioning, we are saying that Spark streaming gives you standard partitioning. Basically, you can give the number of instances of a operator that you want. Spark does support a notion of dynamic partitioning based on some SLAs, but it's a little convoluted, and I'll go into those details. So Spark gives you the ability to exponentially scale up and down the number of partitions of RDD that you have. And this is based on the notion of an exponential increment or a decrement algorithm. For example, for my Kafka input operator, when I start my Spark when I submit my Spark application, I have two instances, two partitions, and then based on some threshold on throughput, I can scale them up to, let's say, 4, then 8, then 16. There's no control to increase them by 1 or 2. It goes in exponents, and Spark takes a call on this on its own. You can specify a check interval after which it will check and see if it needs to increment or decrement the number of partitions that you have. Now, the flip side of enabling dynamic partitioning is the necessity to have state between the newly created partitions and the state that you have had till the point the partitions were created or or just generated, right? So you need a shuffle server for this with Spark, and the shuffle server has to be enabled before you start your streaming application. So if you do not enable a shuffle server before you start your streaming application, what's going to happen is you will not have any stateful executors from that point on after your dynamic partition has been enabled. So every operator has to write to a shuffle server, and then every operator has to read from a shuffle server to be stateful with Spark. Now, this typically ends up becoming a bottleneck because 100 executors are writing to shuffle servers and then to a single shuffle server, and then 100 different executors are reading from that shuffle server to maintain state and really know what processing point they have to start from. For example, let's take the Kafka use case again. I have two operators, each having two partitions, each having read 1,000 offsets from Kafka, and then I partition them into 4. Now I have to start the previous two operators from 1,001 offsets from a given partition, and then I have to associate different partitions of the Kafka topic with the new operators. So this is the kind of state that you want to move to the newly created partitions. Apex gives you very elegant mechanisms to instantiate the new partitions of an operator with some state. Along with partitioning in this context, Apex also gives you unifiers and parallel pipelines, like we saw parallel pipeline schemes with parallel partitioning scheme and M-cross-N partitioning schemes to be able to leverage that. Connector library. So Apex typically, Spark typically relies on limited certification model. So Spark as a Apache project would give you guarantees only with a few external systems that it talks to. There's support for Kafka, for Flume, I believe for Kinesis, and a few others. And all of the other projects around Cassandra, Hive, etc. are externally managed. That means that there are different companies who are basically taking in the Spark code, writing their connectors, and committing it back to Spark. Spark does not give you versioning guarantees when you deal with these systems. Spark only will give you versioning and backward compatibility guarantees with a few of these projects around Kafka and a few others. So that's the model that Spark is following. Apex, on the other hand, believes in complete backward compatibility, even for library operators. So there are a bunch of operators available out of the box with Apex, and you will have very strong backward compatibility guarantees with subsequent releases of Apex that go with the connector library as well. So it's a part of the release process that you ensure compatibility at the operator library level as well. Gonna take some questions if there are any. None at the moment. All right, moving on. Okay, let's take a look at the state management semantics of Spark. So Spark relies on this data structure of RDD, resilient distributed data sets, right? So RDD is an immutable data structure. What it essentially means is that at a particular hop in your directed acyclical graph, there would be an incoming RDD, then that hop would apply a transformation on that RDD, and there will be an outgoing RDD. When that outgoing RDD is emitted from this particular hop or an executor, you would have a state associated with it in terms of lineage. So that outgoing RDD would know who its parent RDD was and what kind of transformation was applied to it. And the current state of data that came with it after that RDD was emitted. For example, let's say I'm doing some parsing and I am taking in a string, and I'm taking in a tuple really, and I'm doing a lookup in my operator and adding one more field to it. So in this case, my transformation is really a lookup, and what I'm writing is one more field, right? So the incoming RDD would have the tuple in itself, and the outgoing RDD would have a tuple with that enhanced field, and a transformation saying, okay, this is my lookup that I've done. Now, in Spark Streaming's case, when this particular executor goes down, what happens is that you have the most current state, and you have a lineage of what has happened before arriving at that state. Now, if you have not executed a persist mechanism, then Spark Streaming would essentially go back, track the lineage, go back to the input operator, read the data back again, and apply all those transformations to arrive at the exact same data that you had. If you have done a persist, then you basically cut the RDD chain, and you actually persist the actual data value and the most recent transformation that you applied to it. You have to explicitly call rdd.checkpoint and rdd.persist to persist the RDD state. Spark gives you different mechanisms to persist an RDD state. You could persist an RDD state in memory, which is again similar to the buffer server mechanics that Apex gives you out of the box. Or you could persist between memory and spill over to disk, or you could spill over to disk only. RDD checkpoints are expensive operations in Spark because you're snapshotting an entire RDD, which is like a table really, per batch. So usually people don't do it at a batch level. They do it based on some time trigger or after multiple batches. What that means is, like, if you're persisting state after every 5 minutes, and if your container goes down, then you have to go all the way back to the input source and replay all of the records, reread all of the records either from an external store or a file system or from Kafka, apply all the transformations, and then arrive at the result that you had. Now, the model that they use to do this is, again, speculative execution, which is typical of any MapReduce systems, right? If a map task fails, then you basically spawn more map tasks in a speculative execution way. So if one map task fails, you'll spawn 3 tasks, and then they'll run in a parallel mode and give you a result. And then you will keep one of the map tasks results and discard the other 2, just to leverage better parallel recovery without spending more time on it. So again, Spark Streaming uses this mechanism of speculative execution for re-executing any failed tasks that it has. Now, Apex uses an incremental recovery model. You basically keep the checkpointed state, and whatever happened in a partial window when the operator went down, you replay those tuples from the buffer server and then apply the previous result from a checkpointed state to the tuples from the buffer server to get the current state of the operator. This works extremely well for achieving end-to-end exactly once semantics. Now, in terms of the processing semantics, Spark Streaming can achieve exactly once, but it's with keywords. So what happens is either you end up doing a lot of RDD persist and RDD checkpoints, or you would have to write all of your transactions or all of the data that you've read to an external storage, read it back, and then basically make sure that you're deduping again between your RDD chaining before you can achieve exactly once. So achieving exactly once semantics with Spark, while it's possible, it's a little convoluted, and even then you can barely achieve end-to-end exactly once semantics with Spark. With Apex, yes, there is an ability to do end-to-end exactly once semantics. On the input and the output operator side, you have to write some user code to achieve end-to-end exactly once, because input-output operators are kind of special operators. They talk to external systems. So if an external system by itself is not supporting exactly once semantics, achieving that with Apex becomes a little difficult. But that being said, all the intermediate Apex operators do support exactly once semantics out of the box. You don't have to write any special code for that. I'll give you an example of an input operator that supports exactly once semantics. It's a Kafka input operator, or a Kinesis input operator, or a file input operator. All of them do exactly once. But let's say you're listening on a socket somewhere and someone is making REST calls on that socket, then that operator would not be end-to-end exactly once, because if the operator goes down and you have sent something or you resend something, then that operator is not going to be exactly once. The same on the output side, you are sending an email to someone. If you're not keeping a track of the emails you've sent, then it's tough to achieve end-to-end exactly once, but at least once will still be guaranteed. Let's take a look at the back pressure. So back pressure in Spark depends on user configuration. It can be threshold or SLA based. Back pressure is basically pushing back records. If something downstream goes down, then the upstream operator basically either stops reading records or keeps it buffered in its own memory until the downstream operator recovers. So Spark streaming, it's essentially batch. So it stops consuming records from external sources once the downstream operators or executors go down. Apex has an automatic mechanism for back pressure. If a downstream operator goes down, then what happens is that Apex keeps on writing, the upstream operator would keep on writing data to buffer server in its appropriate queue. And then if that queue is full, the data would basically spill over to the disk. Since you're running in a distributed way, this typically works reasonably well, because every operator would just be writing, a snapshot to the disk and not, overly occupying the disk anywhere. Elasticity, yes, this is enabled in Spark streaming. It's basically dynamic scaling based on some external throughput. Like I mentioned earlier, this works on the principle of exponential increment and decrement with Spark streaming. So you can only go up in powers of 2 and come down in powers of 2. And the check for elasticity is done periodically with Spark streaming. That periodicity or that interval is configurable, but to really leverage that with a stateful manner, the user has to enable a shuffle server, and the shuffle server more often than not ends up becoming a bottleneck. So while that control has been given to the user, it's usually it's a little convoluted right now, and that has surfaced only in like 1.6. So only 2 releases gone in after that dynamic scaling option has been given with Spark. With Apex, yes, you do have full user control and elasticity. Dynamic scaling is exposed through an elegant scale-up API. The platform inserts unifiers to make sure that after dynamic scaling, the downstream operators don't become a bottleneck. You do have cascading unifiers inserted by the platform also to make sure even a unifier doesn't become bottleneck. So dynamic scaling works very elegantly with Apex. Again, to reiterate, a bunch of operators actually provide dynamic scaling out of the box. Moving on. Okay, I'm going to take a question. A time check, guys. Oh yeah, sure. Luciana, you can have the slides, and feel free to drop in emails to the mail lists given here. Happy to go over it again. Yeah. Let's take a look at what does dynamic topology mean, right? So dynamic topology means the ability to change the flow of your application at runtime. For example, I'm reading some data from Kafka, parsing, filtering, parsing, aggregating, and writing it to a store. I submit this on Spark, and I submit the same thing on Apex. I mean, not the same thing, but same thing in terms of the logical flow. With Spark, once it's submitted, it's done. You can scale up and down, sure, but you cannot insert anything, any operator or any piece of processing into the application once it's submitted and scheduled. The DAG scheduler will keep on scheduling new batches, but with the same application logic. Come to Apex, you actually have an ability to connect to the application master and insert new operators as you go along. For example, with you have the flow of Kafka, parse, then you can add an operator to filter on the fly. You can connect to an application, and then you can insert an operator, change the streams that go on from the parser to the aggregator to make them go from the parser to the filter, and filter to the aggregator to modify a topology at runtime. So on the security front, Apex Spark Streaming supports Kerberos support, which is also native to Hadoop. Apex does support give you Kerberos support natively, leveraging the Kerberos support from Hadoop. And in addition to that, you have role-based access control and LDAP support coming in with the enterprise offerings. Multi-tenancy is the ability of your Spark Streaming application or an Apex application to run with other types of applications. Yes, with Spark, it depends on the cluster manager and it's given. So Spark has three kinds of cluster managers. One is the native one that comes with it. It's usually used for single node deployments of Spark, not for production ones. Then the other one is Mesos, and the third one is Yarn. And Apex is Yarn native, and yes, with Yarn native applications, you get full isolation and multi-tenancy natively. If you recollect, I had shown in one of the earlier diagrams how Apex can run along with your other MapReduce jobs on your data nodes. DevOps tools, Spark Streaming just leverages the Hadoop UIs for it. There is very little control that you can get in terms of your operability semantics with Spark. Usually just basic screens that show you executors running here and there and shuffle going through, leveraging the Hadoop MapReduce APIs. With Apex, you have an elegant REST API that comes with it, even with the community editions. And DataTorrent RTS gives you a way better operational control on how your data is flowing through your application, and basically reports different metrics, both input and output, as well as consumption at an operator level for memory, CPU, etc. Here's an example of one of the enterprise offerings from DataTorrent. Here you've been showcased how a DAG builder would look like. So you can there's a operator palette on the left here, and there's a schema that for providing properties on the operators on the right. So you can literally drag operators into this canvas, connect an operator's output port to the other operator's input port, change properties the way you want to, and launch an application on the fly. Here's how a logical DAG looks like. You have a file splitter splitting splitting a file into different input blocks. The block reader is reading those blocks and emitting some metadata for blocks. Then you can synchronize them and you can merge a file. So this gives you a showcase of both exactly one's reads as well as the ability of Apex to synchronize different blocks while parallelizing the inputs. So you can literally read a single file by splitting it into different blocks and synchronizing it at the output. So parallelism is not just given at an individual file level, but you can actually get a more granular control to read blocks and synchronize them at the end. Again, this is how the application would look like on your cluster at a physical level. You have one instance of the file input splitter, and then 4 of the block reader and 4 of the writer, and a unifier to send all of that data to a block synchronizer, which sends it to the file merger. Here's one of the other enterprise offerings. You can actually visualize in-stream events by creating your own charts using one of the app data tracking mechanisms exposed by the DataTorrent RTS offerings. Few resources that you can subscribe to. We are looking forward to see you on our users and developer mail chains, and just a heat map of where all we are. As you can see, a good amount of spread through the US and Asia. So feel free to join any of these lists. We are very active on the mail chains and happy to see people, more and more people join and contribute. Few business use cases. We have an ad tech company called PubMatic as one of our customers. They crunch ad tech logs to give key performance indicators to track how their advertisement campaigns are running across the globe. The data volumes that they see are 200,000 events per second at least, and we're crunching 22 terabytes in under 30 seconds end-to-end latency. So this is one of the use cases that we have done. GE is another one of our customers who are doing IoT analytics, and they're serving, they're using Apex as the backbone for their IoT platform called Predix, basically analytics on sensor data and IoT logs. Then again, yeah, DataTorrent is happy to see you here. We have a few openings. Feel free to join in. Appreciate you joining us. I will publish the slides and the video. Take care, guys. Happy to see you here. Thank you.